Hi, so I'm Ishmam. So I work with quantum algorithms for quantum chemistry, spin physics, and sometimes biological systems. I am in North Carolina State University as a third year graduate student working with Professor Sabrekais. I was the team leader for Team North America, and we basically simulated radical pair mechanisms on a quantum computer, which we'll talk on later about, I'm sure. Of course, yeah. So we basically, Team North America worked on, as mentioned, simulating radical pair mechanisms on a quantum computer. So what's radical pair mechanism to begin with? So we have birds that we know like migrates every winter and so on. So how do they actually go from one place to another without having like they don't have what should I say definitely they don't pass continents through eyesight alone, right? So they have something that's called the avian compass. That is, they can sense magnetic field of the Earth, and the magnetic field of the Earth changes according to geographic location. So how do they sense this change of like magnetic field of the Earth? It's basically through what we call like spins, or like so there's a special molecule in a bird's eye called cryptochrome, which basically has a spin which responds to the magnetic field. So with the change of the magnetic field, it responds the electrons, or the spins as you call it, responds accordingly, and that's how like birds get from birds migrate. So our project was basically to simulate that, how the spins change according to magnetic field on a smaller scale, since it's a hackathon project after all. It's so we are to a toy model and basically showed that. It initially started off with five, but we had to the team had to be broken down because some team members had other arrangements, so it actually boiled down to two. So it was me from North Carolina University, and there was this another recently graduated undergrad from Northwestern or Northeastern. I think she was from Northeastern. Her name was Shannon. She's I think interning right now at Los Alamos National Lab, and so that was great. So it was us two basically laboring through for the last 2 days, together. So one of the surprising moments is as I mentioned, our project uses a quantum computer, right? So interesting contention or discussion that's going in the quantum computing world is just how useful the current real devices are. And I have all the team members have seen the debates online, but now that we actually got to use some of the noisy quantum simulators or actual quantum devices, we saw that you actually need quantum error mitigation or quantum error correction to actually get to ideal results or classical results. So that's something we always hear, okay, quantum computer is here and ready to change the world. Maybe it is, but you also realize the difference between the classical computers that we have, we are used to using, and the results from the quantum computer, and you see that we are still not quite there yet. So to experience that firsthand while working on a project, instead of just looking at news, it's you can see how far we are off, or what needs to be done to get to, so that both the classical computer and the quantum computer have the same level of accuracy. One of the most interesting things that I would say is hackathons can be super productive, for a research project, the idea is to get small work done in every day. For hackathons, it's so there is a saying that since I'm a grad student, that PhD or any graduate degree is basically a marathon, not a sprint. In this case, it's a sprint, but it's a prolonged a sprint of sorts. So it's but you also get surprised by how much work you can get stuff done when you have 4 to 5 people putting their heads together for 3 days straight and not sleeping. So maybe that's not the ideal situation to go on for for the year, but these small bursts of work, collaboration together is actually pretty helpful. Yeah. The whole experience, I would say, is spending sleepless nights together on Zoom calls, not sleeping, and we had people from the biology background, we had people from chemistry. I'm a chemist by training. We had people from physics, we had software engineers. So people you could see which people according to the background of their how they are trained, approach the same problem in different ways, and that open new avenues to think about. And that's amazing. And also the other thing is that I know people, you could although like I joined virtually, but you could talk to people with similar interests, that is quantum biology, from all around the world on a single platform. That was like, yeah. Me and Shannon talked about it, and I also talked with Pedro, who was also one of the organizers. Pedro gave us some hints to where to go to from here. The obvious next step would be, so we basically followed Pedro's paper for inspiration of the framework that he had. We basically implemented his paper for the hackathon. Is basically to run those on, as I mentioned, we actually ran those on noisy quantum simulators. The next step would be to run them on actual quantum hardwares and try error mitigation and both error correction on those devices on the results we have. And also, talk more to Pedro, who was the original author of the paper, and also Clarice to, see other phenomena regarding radical pair mechanism. Oh, it was wonderful. It was wonderful. I think it's the right step forward. As I mentioned, hackathons can sometimes surprisingly be very, productive. As you can see, we basically implemented a part or reproduced a part of a research paper in 2.5 days, and we already have we are bursting with ideas of what to do next. When Pedro also said, okay, yeah, this is great work for a few days, and we can exchange so many ways. So the thing that I got to talk to so many people from different parts of the world, from different backgrounds, and so as you mentioned, it's the first. So it's definitely the right step to get everyone who is interested in quantum biology to come together, talk, discuss, and something big, so some you could get an off idea or off the charts idea that sounds very small at first, but you don't know, in 3 to 2 years someone would publish a big paper and say, yeah, I got the inspiration, or it started off from this hackathon. So yeah. So I think I already touched on the productivity part of it, how it's productive in short bursts. But I think there was another aspect. Since I talked to people from different parts of the world, was that usually people look for projects, especially high tech or deep tech projects, as you'd say, quantum computing, quantum biology being very niche field, right? So people from where quantum sciences are not as established yet in different parts of the world, right? It's not equally established, right? It's not equitable, to be honest. So, and if people wants to work on quantum biology, they have to get a master's or PhD, which is to get into a master's or PhD is just an year-long application process in itself. But this is an unique opportunity for, for people. I'm from Bangladesh personally, and I had to apply for a whole year to get into this PhD. So for now, if I was an undergrad right now in Bangladesh, I could have just signed up, got into a team, and just learn quantum biology for for a week, and I got to learn something which was off limits. So I think this hackathon was a great equity builder, because masters and PhDs are too long to get into, and also sometimes very expensive. But hey, the hackathon was free. You got to talk to actual professors or industrial researchers who actually work on this, the highest of levels, and you could talk to them, learn for free. Yeah, that's amazing. I think it's the right time to get into quantum biology, because we have, although quantum computers are still yet to match classical computers, but it's getting there, and it's supposed to get there in hopefully next 5 to 10 years. But there are many algorithms which are working right now. We understand much more about the quantum aspects of quantum biology, as to say we have been talking about classical biology, but the quantum effects of biological systems now. The most important takeaway from the hackathon, or if who wants to know about quantum biology, is this is the right time. Because in the past we would say we are too early, the theories aren't developed, there aren't enough tools to probe into what you would call as quantum biological phenomena. But now you have the right tools, you have the close enough or accurate enough quantum simulators. So please get into quantum biology. This is the rightest of time, and the rightest of time to to actually have this hackathon.